Okay, properties of atoms in the periodic table. This is chapter 16, and this is section 3, the periodic table. Organizing the elements. Periodic means repeated in a pattern, okay? And there are patterns to the periodic table that we're going to take a look at. In the late 1800s, Dmitry Mendeleev, a Russian chemist, searched for a way to organize the elements. Now, what it was is Dmitry Mendeleev was a chemistry teacher, and in college, he was trying to get his. We had just been discovering the elements and writing this stuff down, and Dmitry Mendeleev wanted his students to try to memorize this stuff, and they were having trouble. So he created the periodic table. All right. And he created it as a cheat sheet. So to learn the periodic table, that takes a lot out of you, trying to learn that periodic table and memorize it. It's easier as you work with it, especially if you'll take chemistry class. You'll notice the more you work with it, you'll memorize it. It just happens kind of automatically. But his students were having trouble, so he created the periodic table. And when he arranged all the elements known at that time in the order of increasing atomic masses, he discovered a pattern. All right. Organizing the elements. Because the pattern repeated, it was considered to be periodic. Today, this arrangement is called the periodic table of the elements. In the periodic table of the elements, in the periodic table, the elements are arranged by increasing atomic number and by changes in physical and chemical properties. Now, remember, the original was by the atomic mass. Okay, but as we discovered more and more elements, we ended up having to change it to the atomic number for it to work out right. Okay, so Mendeleev's predictions. Mendeleev had to leave blank spaces in his periodic table to keep the elements properly lined up according to their chemical properties. He only had, I believe, 61 elements, and I don't even know if he had that many, but now we know there are way more. There's up to 114 elements, but back then there was only 60 maybe, and he put them in order of their atomic number. Now, in these blank spots on his periodic table, he could kind of guesstimate what was going to go in those blank spots. He looked at the properties and atomic masses of the elements surrounding the blank spaces, and from this information, he was able to predict the properties and the mass numbers of the new elements that had not yet been discovered. All right, so the improvement of the periodic table. In 1913, the work of G.J. Moseley, a young English scientist, led to the arrangement of elements based on their increasing atomic numbers instead of arrangements based on atomic masses. The atom in the periodic table. The current periodic table uses Moseley's arrangements of the elements. The vertical columns in the periodic table are called groups or families and are numbered 1 through 18. Elements in each group have similar properties. A neutral atom. In a neutral atom, the number of electrons is equal to the number of protons. And remember, that is the atomic number. Therefore, a carbon atom with an atomic number of 6 has 6 protons and 6 electrons. Remember that the atomic number found on the periodic table is equal to the number of electrons in an atom. So that atomic number, the atomic number is equal to the number of electrons. Let me pull up that periodic table. All right, so here's the periodic table. The families are groups. Let's go up here. Here's the families, 1 through 18. The families are right here. These are families or groups. Families or groups. Okay, right here. Vroom, 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 vroom. These are my families in groups. Now, the atomic number, right here, it's talking about carbon, 6. There are 6 protons and 6 electrons. Okay, 6 protons and 6 electrons. Nitrogen has 7 protons, 7 electrons. Fluorine, 9 electrons. Okay, 9 electrons, 9 protons. So remember that the atomic number found on the periodic table is equal to the number of electrons in an atom. Rows in the periodic table. The first row has hydrogen with 1 electron and helium with 2 electrons, both in energy level 1. Let me pull this back up, and here you go. Here's my energy level. These are periods. These are periods, okay? Vroom, vroom. And when it's talking about energy level, this is the first energy level. Here's the second energy level. These have 2 energy levels. These have 3 energy levels. These have 4 energy levels, okay? What does that mean? You're going to find out as we're going along here. So the first row has hydrogen with 1 electron and helium with 2 electrons, both in energy level 1. Energy level 1 can only hold 2 electrons. Therefore, helium has a full or complete outer energy level. And if you're questioning this, you need to read. You'll read about the energy levels and you'll understand them. So the second row begins with lithium, which has 3 electrons, 2 in energy level 1 and 1 in energy level 2. Lithium is followed by beryllium with 2 outer electrons, boron with 3, and so on until you reach neon with 8 outer electrons. Rows on the periodic table. Do you notice how the row in the periodic table ends when an outer energy level is full, or an outer level is full? In the third row of the elements, the electrons begin filling orbit 3. The row ends with argon, which has a full outer orbit of 8 electrons. And again, you guys, if you're not catching this, you need to look at the book and read the pages in the book. That brings up electron dot diagrams, okay? Elements that are in the same group have the same number of electrons in their outer energy level. These outer electrons are so important in determining chemical properties of an element that a special way to represent them has been developed. And it's called the electron dot diagram. And it uses the symbol of the element and the dots to represent the electrons in the outer energy levels. Electron dot diagrams are used also to show how the electrons in the outer energy level are bonded when elements combine to form compounds. Same group, similar properties. And this is why it's called a family. I'm going to show you really quick here why they're called families. All right. The elements in group 17, the halogens, have an electron dot diagram similar to chlorine. All halogens have 7 electrons in their outer energy level. Okay, so these 7 electrons, and this is my dot diagram. Okay, again, if you're confused on this, you need to read the book. Okay, need to read it, then come and watch the notes. So the reason they're called families, ladies and gentlemen, is because if we come down here, I wrote how many dots or electrons are out in that outer energy level. That's what these numbers are. 1, 2, 3, 4, 5, 6, 7, 8. All elements, all of them want 8 electrons, except for, remember, hydrogen and helium only want 2. Okay, hydrogen and helium only need 2. So helium is actually a 2, but the rest of them here are 8s. So we have 1, 2, 3, 4, 5, 6, 7, 8 outer or valence electrons. These combine to form the number 8. Okay, so if I have aluminum oxide, or not aluminum oxide, aluminum nitride. 5 plus 3 is 8. There'll be one aluminum atom and one nitrogen atom because that equals 8. And we're always looking for 8 or a combination of 8, all right? Or a combination of 8, like 16, 32, 24, anything that is 8. We're looking for combinations of 8. Now, chlorine has 7 electrons. Chlorine has 7 electrons. Here's chlorine right here. 7 electrons. The reason it's called a family is because all of these that are in green have 7 outer electrons. All of these have 6 outer electrons, 5 outer electrons. These whole families have 4 outer electrons, 3 outer electrons on that outside energy level. These have 2, and these have 1. That's why they're called groups and families. The other thing I want you to look at here too is, and I usually go with this one right here because we're all pretty familiar with these. Carbon. If you get a piece of charcoal, which is mostly carbon, it's black. Silicone is a grayish black. Germanium, grayish black. More gray now. They're black, and as you go down, they get more gray. All right. So carbon, silicon, germanium, tin. We know tin's gray and lead is gray. They're a family. They're similar to each other. Okay. If we look at this family, and I know we don't study this family, but I think I've probably brought this up before. Copper. It's a nice, shiny, bendable metal. Silver. Nice, shiny. We can bend it. And the same with gold. They're in a family. They're similar to each other, okay? Here's iron. What color is iron? Is like a gray color, so you can pretty much imagine all these are going to be in a gray tint, have a gray tint to them. And that's what's so cool about the periodic table and the families, all right? And Mendeleev noticed this. Mendeleev noticed this, these trends, and they periodically repeat themselves. The table periodically repeats itself. It goes up to the number 8. It goes up to the number 8. It will go up to the number 8, up to the number 8. Okay? And we could go like this too. 1, 2, 3, 4, 5, 6, 7, 8. And sometimes there's a bracket. I don't know if there's one up here. There's not. But 1, 2, 3, 4, 5, 6, 7, 8, 8, and 8. These 3 columns have 8 valence electrons already. Then we start over. 1, 2, 3, 4, 5, 6, 7, 8. The reason I have these highlighted, though, only these, 1, 2, 3, 4, 5, 6, 7, 8. This area in here is completely and totally different. These are called transition metals, and they don't work the same as the rest of the periodic table. I've had a lot of college chemistry. I've had a lot of college chemistry courses, high school. I've taught chemistry. You will never, unless you take a specialized class in college, you'll never even look at any of this stuff. Okay? You're only going to be concerned with these 8. If you take organic chemistry deals with these 7. 1, 2, 3. They form the number 7, and there's 7 of them. 1, 2, 3, 4, 5, 6, 7. Anything that lives, anything that has life or is organic has these 7 in it. These 7 make up life. Okay. So all halogens have 7 electrons in their outer energy level. Same group, similar properties. A common property in the halogens is the ability to form compounds readily with elements in the alkali group. Why? Well, check it out. 7, 8. Alkalis have 1. Halogens have 7. So they readily form compounds with each other. Same group, similar properties. The elements in the noble group have a complete outer energy level. The special configurations make group 18 elements unreactive. So let's take a look at group 18. Here's family or group 18. And we come down here, they already have 8. And since they already have the number 8, they do not react. All right. If you put hydrogen in a balloon and light it, it'll explode. If you put helium in a balloon and touch a match to it, nothing happens. When you inhale helium, it's not going to hurt you. It might make you a little lightheaded, but it's unreactive. It already has all of its electrons. So it's not going to react with anything in your lungs. All right. It's okay to do it. It'll give you a headache, or it might make you lightheaded or dizzy. It changes your voice, which is really cool. But it's unreactive because it already has all of its electrons. You guys have noticed my Spider-Man comic book covers in the background here. This is my favorite guy, Kraven the Hunter. The horizontal rows on the of elements on the periodic table are called periods. So again, we have families right here, 1 through 18. That's this, up and down. And then periods, which go side to side. And there's 7 of those. There's 7 periods. 18 groups or families, 7 periods. These elements increase by 1 proton and 1 electron as you go from left to right in a period. So let's look at this again. 1 electron, remember, there's my number. 2 electrons, 3, 4, 5, 6, 7, 8, 9, 10 electrons. Sodium has 11. Magnesium 12, 13, 14, 15. So I have, as I go from left to right, I increase 1 proton and 1 electron. Remember, as I go down a family, as I look at a family, they all have the same number of outer electrons. So these all have 7 on the outside. These all have 6 on the outside. These have 5, 4. And that outside is called the valence, all right, the valence electrons. So again, as I go from left to right, I add an electron. As I go down, all of these electrons have the same numbers. Of course, helium and hydrogen, remember, there's only 2 in those. All right, regions of the periodic table. All the elements on the left side of the staircase are metal or metalloids. Those elements on the right side of the staircase are classified as non-metal. So let's take a look again. That's why I put this staircase here. Okay, everything on this side is a metal or metalloid. These are all non-metals. Everything over here is a non-metal. That's what this staircase is for. Right here, this staircase tells us that there are nonmetals and metals. In 1994, scientists at the Heavy Ion Research Laboratory in Darmstadt, Germany, discovered element 111. Element 112 was discovered at the same laboratory as is 113 and 14 and so on. Both of these elements are produced in the laboratory by joining smaller atoms into a single atom. Okay. And this is really key because they're going to start talking about the elements in the universe and the Big Bang. And you guys, I'm sure, know how I feel about the Big Bang, but let's just take a look. What they're getting at here is this. When there was an explosion, the Big Bang, the only elements available at that time were hydrogen and helium. Okay. These were the 2 that were involved in the explosion. But at the right temperature and the right pressure and the right speed, if a hydrogen and helium atom hit each other, they'll combine to form a lithium atom. If a hydrogen hits that lithium atom, I get a beryllium. If a helium hits that lithium atom, I end up with boron. Okay, helium 2 plus 3 equals 5. And we're looking right here at the atomic numbers. So everything came from hydrogen and helium. And what do you think are the most um, plentiful elements in the world? Well, hydrogen and helium. So we believe that all this combination down here, according to the Big Bang, they believe that all these elements were formed from hydrogen and helium originally. So, using the technology that is available today, scientists are finding the same elements throughout the universe. Many scientists believe that hydrogen and helium are the building blocks of other elements. Exploding stars or supernovas give scientists evidence to support this theory. Many scientists believe that supernovas have spread the elements that are found throughout the universe. And a supernova is nothing more than an explosion or a big bang. Questions. How are the elements arranged in the periodic table? They are arranged according to their atomic number. What do the elements in a vertical column on a periodic table have in common? They have the same number of valence electrons: 5, 6, 7, 8, 3, 4, 1, and 2. And what do the dots in electron dot diagram represent? They represent valence electrons. Valence electrons. Make sure you read. To completely understand this, you're going to have to read it. So make sure you read it, then watch this over again if you have to, and then complete the work. Have a great day.